Yeah. Yeah, so the thing we're going to talk about today are like the most important things, like concepts there are, because I mean, after manifolds, of course, um, because all the physics takes place with objects like this in mind. Okay. So we are one step away, essentially, from being able to talk about physics, being able to talk about whichever, like whatever type of physics we want to talk about. Um, okay. So, and that's the topic of fiber bundles. Fiber bundles. Okay. But we'll spend most of today's like meeting on vector bundles. Yeah. We will spend time today on vector bundles. And the way we're going to motivate this topic is we're going to start off with we're going to see how we can take a collection of data. Okay. I'll define more precisely what that means exactly. We'll take a collection of data and then we'll patch these up together in such a way that we get a useful object. Okay. So let's see what that means. So I want to start off with my manifold, okay? So let um, let M be a smooth manifold, and let U alpha, phi alpha be an atlas, okay? Be be an atlas for M. So we talked about what it means for this to be an atlas and so on. And now what we're gonna do is we're gonna pretend as if we don't know what M is. Okay, and we're gonna try to take these maps, sorry, this data, okay, and we're gonna try to construct M back from this. Okay, we're gonna try to work backwards now. So, because in many situations, what will happen is we will have this collection of objects, and we'll need some way to piece them together to get a smooth manifold at the end. Okay, so let's begin with that. So step one is, well, we combine everything into one. Okay. So we start by, so we said y equal to the disjoint union over alpha of u alpha. Okay. And all this means is you stack the like sets on top of each other. So even if you have two of the same sets, it's fine. There's still two distinct sets in this case. Okay. Another way to look at this is as a set. Okay, this is as a set. This is the same as um, the collection of all alpha and u alpha. All alpha and x, where alpha is in A and x is in u alpha. Okay, so you should be able to distinguish that x came from this set specifically. Okay, this is different from the Cartesian product because in the Cartesian product, sorry, this is different from the union, like the regular union, because you don't actually know which set every point came from. Okay, but in this case, you're specifying that the point x came from u alpha. Okay, now what we're gonna do is we're going to okay, so we have this, so we just have we've stacked up all these like open sets together, but there's no way to there's no way for me to recover M from here Sorry, let me word this slightly better. Now that I've stacked them all together, I need a way to glue them together, right? Um, so it's like I just have a bunch of sheets of paper, okay, that don't touch each other. Now I need to assign a rule so that I can take two sheets of paper and then join them in such a way that I patch everything together to get my manifold. Okay, that's the idea. And the way we do this is we define an equivalence relation on this set. Yeah. So we want to patch the U alpha together in such a way um, so that we recover M. Because as of right now, is everything's just on top of each other. So even if U alpha and V alpha, for example, they intersect, that intersection is not shown um, in this disjoint union. Okay? So their topology is, obscured. Okay. To do this, we define an equivalence relation on Y. Okay. And the equivalence relation that we're going to choose is going to be as follows. So we first note that um oh wait, I have made a mistake. So I actually want this to be phi alpha view alpha. And then this tells me that x is in phi alpha u alpha. So these are subsets of Euclidean space. I made a mistake there. My bad. And now what we're going to do is we're going to define an equivalence relation on Y as follows. So just for notation's sake, we're going to call V alpha. Um, and by the way, everything that I'm doing, if you want to read more in depth about, um, I'm essentially following this book called Classical Principle Bundles by Stephen Santz. It's in the lecture notes. So if you want to um follow his definition, like his construction slightly closer, then you should go check that out. Okay. So with that out of the way, okay, so we're gonna define for notation's sake, we're gonna say V alpha is equal to these subsets, phi alpha, U alpha. Then we'll define V beta alpha to be phi alpha of U alpha intersect U beta. Okay. So alpha alpha and alpha, beta beta. Just so that we don't get confused later on, I'm gonna also define V alpha beta, just so that we're more happy with this definition. Phi beta of U beta intersect U alpha. Okay. Then the transition functions psi of beta alpha, they go from V of beta alpha into V of alpha beta. Okay. So if you remember, the transition functions are defined by psi of beta alpha is equal to phi of beta composed with phi of alpha inverse. Okay. This is just the definition of the whatchamacallit. This is just the definition of the transition functions. Okay. And now we're ready to define the equivalence. So we say that um, x in V beta alpha is equivalent to y in V alpha beta if so okay, so the first thing is like the equivalence has to has to glue together all the points that are the same. So points that we've overcounted, right? We need to glue everything into one point. Okay. One way to see this is okay, if I had two disks, okay, and they intersected right like in some small area over there. In my construction right now, I just have these two disks sitting on top of each other, but they don't touch. Okay, they're sitting on top of each other, but they don't touch. But so to make them sit like this, we have to identify this small portion with this small portion, right? So if I drew it out, say I had disks that intersect like this, they intersect over here, right? But in our construction, but we have so I'll call this A, I'll call this B. So in our construction, we have A and B sitting on top of each other like this. Okay, they're not touching. So what we need to do is we need to identify this portion of B with this portion of A, right? If I identify these two portions together, what happens is that the resulting thing looks something like this, right? Where they have their like common intersection, um, where they're glued on their common intersection. So this is what we're going to take inspiration from. And so two things are equivalent only if they're related by a change of coordinates, right? Because we're describing the exact same points, but just in a different coordinate system. Okay. So if y is equal to, so we look at a change of coordinate system, but a change of coordinate system was given by the transition function. So this means it is related like this. Okay. And just to be more explicit, this is phi beta composed with phi alpha inverse of x. Are there any questions on why we've defined this equivalent, like this relation, to be this way? Okay. Okay, so I've already given away the secret here that this should be an equivalence relation. Um, and for a change of pace, we're actually going to prove it. Okay. It's been a while since we actually proved something. So let's show this. Okay. Let's do that over here. Okay. So what are the key ingredients we need for this to be an equivalence relation? So we need to show that x is related to x, okay, as usual. So I'll let me number these. So this is one. This is x is equivalent to x. Number two is if x is equivalent to y. This is if and only if y is equivalent to x. Okay. And then the final thing is x is equivalent to y and y is equivalent to z, then x is equivalent to z. Right? This is what makes the relation an equivalence relation. Okay. Now let's show this. So let's show one. I okay, so this is very trivial. So if x is in V alpha alpha, then um then psi alpha alpha is just like phi alpha composed with phi alpha inverse is the identity map. So identity on Rm. But then x is equal to the identity on Rm of x, which is phi alpha inverse applied to x, which is psi alpha alpha of x. So they're related by a change of coordinate, which shouldn't be surprising. Okay. That x and x are related by a change of coordinate. So hence x is equivalent to x. Yep. Number two, if x is in V alpha beta and y is in v, oh sorry, this should be beta alpha, alpha beta, with x equivalent to y, this means that y equals psi of beta alpha on x. But let's look closer at what psi of beta alpha is. So this just equals psi of beta, sorry, phi of beta composed with phi of alpha inverse on x. Now, the defining properties of the phi alphas, are that they're invertible, right? Which means that, hence, if I just take the inverse of this map, which the inverse of this map would be, hence note that if I look at psi alpha beta of y, psi alpha beta of y is nothing but phi of alpha composed with phi of beta inverse on psi of beta alpha of x, right? Because this is just y, right? So I just replaced y with this because of this equation. If you FOIL this out, this is phi of alpha, phi beta inverse of phi beta of phi alpha inverse of x. Sorry for so many brackets. But this phi beta inverse and this phi beta cancel out. And what you're left with, did I make a mistake? Is no, yeah. So this cancels out with this. So what you're left with is phi alpha and phi alpha inverse, but these cancel out. So what you're left with is just x, which tells you that x equals a transition function on y. Yeah. Which then hence y is equivalent to x. Okay. Are there any questions on these two properties so far? Okay. Now, okay, let's move on to the other one. The second one, oh sorry, the last one. This one's also just an annoying computation. So if x is in v beta alpha, y is in v gamma beta, and z is in v beta gamma. Okay, so let's work through oh yeah, and x is equivalent to y and y is equivalent to z. One thing we now have to note, right, is if x and y are equivalent, that means y has to be in the image. So y has to be in the image of this, right? Y has to be in here. Similarly, but we've also said that y is in v gamma beta and y is in v gamma beta. Um, since it's in gamma beta, what this tells you, it has to be in beta of v beta inverse u gamma, right? Which then tells you that y is in the intersection of all three of these sets. So which tells us that we are looking at the case where u alpha, u beta, u gamma all intersect. Okay. This is more of a technical detail that doesn't really need to be mentioned too much. But it'll make the compositions that we define in just a moment make sense. Yeah. Okay. So we know that y is equal to psi beta alpha of x. And we know that z is psi gamma beta of y, which then tells you that z is nothing but psi gamma beta of psi beta alpha of x, right? Because you can just replace y with this. And now expanding out this definition, you see that this is phi gamma composed phi gamma of phi beta inverse of phi beta of phi alpha of x. And again, there's like 400 brackets. Okay. All I've done is I've expanded this because this is phi gamma phi beta inverse. This is phi beta phi alpha inverse. Okay. Are you okay with this? Okay.
Yeah, yeah.
And now this phi beta inverse cancel out, and all you're left with is phi gamma composed with phi alpha. Sorry, this should be inverse. Alpha inverse of x, but this is nothing but psi gamma alpha of x. Hence, z is say x is equivalent to z, just as we needed. This means that this twiddle is an equivalence relation on y. Okay. Are there any questions regarding what this equivalence relation is doing? No. Okay, very good. Um, excuse me. With this out of the way, let's now so now let x equal y with this equivalence, which is nothing but the set of all x in sorry, set of all equivalence classes of x in set of all equivalence classes of x where x is in y. Yep. So far, all we've done is we've taken all this data and we've combined them in such a way that two pieces over like we make the overlapping pieces actually overlap instead of just stacking them on top of each other, non-interacting. And we haven't given it any topology, right? There's no topology that we've given so far because we don't know what the topology we don't know what the topology of this disjoint union then quotient should be. So let's do a quick aside on the topology of the disjoint union and quotient. So a quick aside. So the topology of disjoint unions and quotients. Okay. Let's start with disjoint unions because I feel like disjoint union topology is very simple. So suppose um suppose you had A is just a disjoint union of V alpha, where alpha comes in some index set. Moreover, it's important that all these V alphas are topological spaces. Yeah. Yeah. They're topological spaces. So that matches the situation we have here because each of these U alphas, they have a topology given from M, right? You just restrict the topology to the set, and that gives you the topological space. Also, each open set in Euclidean space has a topology of its own. Okay. Then let's visualize this, right? So then we may visualize A as so the idea is it's a stack of pancakes, okay? It's a stack of pancakes. Uh, Pancakes that don't touch each other. Okay. They're just on top of, they're like levitating on top of each other. So you have something like this, and like this, and like this, and so on. Okay, so this is, I don't know, V alpha, V beta, V gamma, and so on. Okay. They're just on top of each other. So now if we take a set, now if B is a subset of A, okay, then B is open in the disjoint union topology if and only if B intersected with each of the V. So if I look at the intersection of B with each of the pancakes, okay, that section has to be open, must be open in V alpha. Okay. So what do I mean by this? So let's say we took our space, let's say this was our subset B, okay? If we look at this intersection here, it looks something like this. Now what we require is that B intersect V beta. All we're requiring is that this subset be open in V beta. Okay. I know it's a very bad drawing. I'm sorry about that. But just imagine that this is B intersect V beta. Okay. So B just takes in chunks from like every single slice of pancake. It doesn't have to, right? It certainly doesn't have to. But in this case, it does. Let's say. Okay, so that's the disjoint union topology. It's very simple. You take a set, you look at its intersection with each slice. If that intersection is open, it's open. Another way to look at this is we have maps. So another way to look at this. So we have maps, iota that I'll say from V alpha into A, right? They take a point X and they map you into alpha X. Okay. Now what we're gonna say is that A has the topology that makes every map iota alpha continuous. Okay. And it's the smallest such topology that does this. Okay. Then smallest or biggest? It's the biggest such topology. So it's the coarsest. Sorry, it's the finest such topology. Then A has the largest topology that makes all maps iota alpha continuous. Okay. Um, I forget the name. This is either called the initial topology or the final topology. I forget which one. Okay. Are there any questions about the topology on the disjoint union? Okay. So, um, okay. Now let's look at the quotient. So let A be a topological space. Topological space. And let um, twiddle be an equivalence relation on A. So let B be, A quotient B. Sorry, A quotient this twiddle. So now the question is, what is the topology of B? Um, Let me write this on the other one. Let B equal A quotient the twiddle. Now the question is, what is the topology on B? And the topology on B is very simple. So we have a map Q from A into B that takes a point X and maps you into the equivalence class of X. All we require is that B has the largest topology that makes this map continuous. Then B has the largest topology so that Q is continuous. Okay, because there's a bunch of topologies that'll make this continuous, right? If I take the topology of just the empty set in B, that forms a topology of B. And in that case, um, this map will be continuous, right? But that's not really useful, right? That's not a useful topology on B. And so the most useful topology on B that we can get is the one that has the most open sets, respecting the property. Okay, so are there any questions on like what the different topologies are?
Sorry, can you explain like the last bit again?
Okay, so there are many topologies on B that make the map Q
Yeah.
continuous. Right? One of
Yes.
the examples of such a topology would be the set, so would be the topology with the empty set and all of B. With only, so we only have two open sets. And if you recall what the definition of continuity was, is that when we took the pre-image, we want that to be open. But the
Mm-hmm.
pre-image of the empty set is empty, and the pre-image of the entire
Mm-hmm.
set would be A, because the map Q is surjective, which then means that um, which then means that the map is continuous because both those sets are open in the topology of A by the definition of
Mm-hmm.
topology. But this topology is not useful in the slightest, right? Because it has a very
Mm-hmm.
few amount of um, it has such a few amount of sets, open sets, and one can show that every map would be continuous because the pre-image of the entire set would be the entire domain. So every map is continuous, which is not too useful, right?
Yeah.
And so we restrict ourselves, we add the restriction that this has to be the biggest such topology that makes this happen. You might run into a situation like where you have the discrete topology on B, and that might not make the map continuous. So that's too big a topology. Yeah. So I hope that
Okay.
answers your question.
Yeah. Thank you so much.
Okay. Okay, so yeah, with this quick aside on topology aside, we now get that X, if you use some like theorems from topology that we will not like we will not we will not think about too much. Um, X is a topological manifold. Okay. Moreover, one can show that as topological manifolds or as topological spaces, M and X are homeomorphic. Okay. So we've successfully recreated um, the topological space M just from local data. But now the question is, okay, that's fine. It works in the case of topological manifolds. Is there a way that I can take the um, smooth structure of M and make it into a smooth structure of X, right? Because remember, we want X to be the same smooth manifold as X, right? And the way we and the answer is yes, right? So yes, you can. It turns out that if you have any two homeomorphic spaces, then and one of them is a smooth manifold, the other one can be made into a diffeomorphic smooth manifold. Okay. And it's very simple. So let F from M into X um be the homeomorphism. Okay. One second, sorry. Yeah, so let be the homeomorphism. Then oh yeah, and let U alpha phi alpha be a chart. Sorry, be an atlas. be an atlas of M. Okay. Now the idea is we push forward these atlases. Okay. And the way we do this is note that F of U alpha as a subset of X is open. And the reason for this is because F inverse is continuous. Okay. Since F inverse is continuous, the images of open sets have to be open. Okay, so we have this. Then consider the map phi alpha composed with F inverse. Okay, this now takes you from F of U alpha into U hat, which is equal to phi alpha of U alpha, as we defined it before. Then this is a homeomorphism. And the reason it's a homeomorphism is because it's a composition of two homeomorphisms. Now, the transition functions, the transition functions are given by, well, okay, so I have to take one of the things and then I have to compose it with the inverse of the other one. So I have to look at this, but this composition is very easy to compute out, right? You just get this. 2, and this gets you, so the F inverse and F cancel out, and all you're left with is phi beta composed with phi alpha inverse. But since M was a smooth manifold, you know that these transition functions are also smooth, which then means that your atlas then um F of U alpha with phi alpha composed with F inverse is a smooth atlas for X, right? And since it's a smooth atlas for X, um, you then know that you can extend this into a smooth structure on X, making X and M into diffeomorphic smooth manifolds. Extending to a smooth structure on X, we get M and X are diffeomorphic smooth manifolds. Okay, are there any questions on how we have reconstructed M um, from its charts, essentially? Okay. Because this is now going to be a very, very important concept. What we're going to do now is we're going to take local data that satisfies the conditions um, of the things here, um, in the sense that we have a collection of sets. We have on the intersection, we have a collection of transition functions that satisfy the conditions for them to be an equivalence relation. Okay, and then we're going to glue them together to get a new smooth manifold. Okay. So let's now let's now look at an example of this construction. And we're going to use this on the most important manifold associated to a manifold, and it is the tangent bundle. The tangent bundle. So, as the name suggests, the tangent bundle is the bundle of all tangent spaces. Okay. I know, very, very profound naming there. But to do this, we first have to know what the tangent bundle of open sets in R is, or Rn, right? So first, what is the tangent bundle? Sorry, my handwriting is bad. Tangent bundle, tangent bundle. What is the tangent bundle of open subsets of R? Right, because, okay, now we know that, okay, it has to coincide with what we know from multivariable calculus. Okay. And so the way we define the tangent bundle of open sets is we say, okay, if U is an open set, it's just the disjoint union of points in U of all the tangent spaces. Right? That's what it is. Simple. Now, one thing to note is that even as a manifold, this thing is the same thing as U times Rn. And the reason for this is because as we will see later on, the equivalence relationship that we give between these two things is if they're the equivalence relation that we'll give on this set is 2 points are the same if they're related by a change of coordinates, right? And because U is an open set, we have a change of coordinates. We have the identity change of coordinates. Okay. We also have a change of coordinates that maps one point to any other point. Okay. Which means that every tangent vector is going to be the same as every other tangent vector at some other point. In what happens is that the tangent bundle then collapses down to something very nice. Right? It just collapses down to this set. But as we will see, especially in the case of the sphere, okay, the sphere is the first non-trivial example that comes to mind, where the tangent bundle does not decompose like this. Okay, so the tangent bundle of a sphere, I'm just going to make a note here. Note, this works since U is an open subset of Rn and the transition functions are quite nice. As we will see later, the tangent bundle of the sphere is not S2 cross R2. Okay. It turns out that the tangent bundle of the circle is S1 cross R. Um, but unfortunately, it doesn't carry on further than that. I think the tangent bundle of S3 is also S3 cross R3. Um, but we will show that if your manifold is a Lie group, then its tangent bundle does decompose like this. Okay. So if also we will see that if M is a Lie group. Wait, I guess you weren't there when we defined what a Lie group was, right?
No,
Okay, I'll define that in just a second again. So if M is
that's
a
what
Lie
I
group,
think.
then Tm is equal to M cross R. M. Okay, so a Lie group is a manifold. Okay, so it's a smooth manifold. Whenever I say manifold, I mean smooth manifold. Okay, I'm not gonna write smooth every time. Manifold plus group. So it's a manifold and a group. Um, such that um, multiplication and inverses, well, inversion is smooth. Okay. So you have the multiplication map that takes two things and multiplies them, and you have the map that takes an element and gives you its inverse. So if both of these maps are smooth, then your manifold is a Lie group. So an example of a Lie group is Rn with addition, right? Because addition is smooth, and if I put a negative sign, that's also smooth. So in the case of Lie groups, the tangent bundle decomposes very nicely. Okay. And we will see that, and what this actually then tells you is that S2 is not a Lie group because its tangent bundle does not decompose nicely. Okay. I don't know if the converse is true. I don't know if if the manifold, if the tangent bundle of the manifold decomposes. I don't know if, um, you know, but okay. That's just a note though. With this out of the way, let us now, so let's now define like all the things we need to. So let M be a manifold with atlas, well, smooth, because I guess it's sort of important here. With atlas, with an atlas, U alpha, phi alpha. Okay. Then we will call, okay, so each U alpha is um a subset. Sorry, it's an open subset of M, right? Moreover, each U alpha is diffeomorphic to an open subset of each U alpha is diffeomorphic to an open subset of Rm, which means that their tangent bundles should be the exact same thing. Okay. Are there any questions on that? Okay. So then we define the tangent bundle, sorry, the tangent, yeah, tangent bundle of um T, actually, sorry. Then we take as our sets the tangent bundle of phi alpha U alpha. Okay. This is what we take as our collection of sets. So okay, we've given a collection of sets. Now we need to give a now we need to give now we need to give a gluing between them. So when these two things intersect, how do we glue them? And since we're looking at the tangent bundle, it's most obvious by the chain rule. So since we know that for tangent vectors, chain rule has to hold. By the chain rule, the only map that we can give between tangent spaces, right, between these tangent bundles, has to be the derivative of the transition function. Does that make sense? This is a very important concept. Okay, so now we glue. So now the transition functions over this uh the transition functions between overlapping tangent bundles has to be, we have no other choice. It has to be. Um to be the derivative of the map of the transition function psi beta alpha from u alpha u beta into phi beta u beta u alpha. Okay. There's no other choice for this. Now, as we will see later on, there are many other choices that we could have made, right? Um, there's nothing special about this transition function, but we want tangent vectors to behave like tangent vectors. And one thing we know about tangent vectors is that by the chain rule, when we do a change of coordinates, their components change by the components change by the derivative of the transition function by chain rule, right? So to get a good collection of all the tangent vectors, the only thing we can do is look at the transition function between the underlying sets and then take its derivative. But I'm going to define um, the derivative slightly differently. And I'll call this the tangent derivative for now, or the tangent map of the derivative, or whatever you want to call it. And it's going to be defined as follows, okay? So it's going to be the map T psi beta alpha. And what it does is it goes from the tangent bundle um, of U alpha intersect U beta into the tangent bundle of phi beta of U beta intersect U alpha. Okay. What it does now is it takes an element x comma y, which is an element of phi of U alpha. Okay, I need more space. So it's Rm here, and then it's U beta intersect U alpha phi alpha, which is then itself a subset of R to the 2m. And then it maps it over to phi beta alpha of x. And then we just take the derivative of the transition function at x, evaluated at y. Okay. And note that this is a very this definition should make sense from the previous section because x is now related um, to the transition function applied to x. So we have the so this sort of respects the structure of the manifold itself, right? From our construction above, um, with this, right? It respects this um, structure of the manifold itself. And it adds the additional structure that y has to be the same thing after a change of coordinates by the derivative of the transition function. Okay. So with all of this out of the way, we now construct, so now define the tangent bundle on M. Okay. And by the same logic that we used to prove the other stuff, this will now be an equivalence relation. Okay, so let's actually before we define this, let's actually write out the equivalence relation. So like more precisely. So we say that x in the tangent bundle of this and y in the tangent bundle um, like this are equivalent if and only if y equals t psi beta alpha of x. And then using chain rule and the exact same logic we did in the previous section, this map is a equivalence relation. And so we can define the tangent bundle. So now we define the tangent bundle Tm to be, okay, so we take the disjoint union of the tangent bundles of phi alpha. Okay. and then we quotient out the equivalence relation. Okay. And this is now the tangent bundle on M. It looks very complicated, right? It looks very complicated. However, it's very simple, right? It's just saying, okay, you can be at a point, and then at this point you look at all the tangent vectors. And the best way to interpret what this definition is, right, is if you have some coordinate system on M, right, then the tangent bundle of this coordinate system is just that coordinate system crossed with Rm. And the reason for that is, well, we defined it to be that way. Okay, it's defined to be that way. And so in that case, any tangent vector, right, is just written as a linear combination of functions on M or on U on the open set times the coordinate tangent vectors that we defined previously. And this is what physicists mean when they say that vectors transform like vectors. Okay. This is precisely what they mean. So let's write this out a little more carefully. So we're gonna the vectors transform like vectors is equivalent to saying that a vector or a tangent vector at one point is equivalent to another tangent vector if they are related by a change of coordinates. Okay. And this sort of demystifies the that definition of a tangent vector or a vector in the first place. And it also gives you that, for example, the magnetic field is not really a vector in this sense. Okay, it's not a tangent vector. Okay. In some sense, it's a pseudo vector. We'll define pseudo vectors in a bit, but not in. We'll probably define it next time. Um, but yeah. So okay, let's write out what it means for things to be equivalent in a chart. So if so let's say we have the point phi alpha x and v as a subset of the tangent bundle of phi alpha, right, which is just equal to phi alpha times Rm. Um, then this is equivalent. This is equivalent uh, to T psi beta alpha of phi alpha x v, which by our definition is just psi beta alpha of phi alpha of x, and then the derivative of psi beta alpha at phi alpha. Okay, I didn't realize I'd run out of space. Is equivalent to of x, and then you evaluate this at the point v, which which computes out to phi alpha x v. So a tangent vector like this is equivalent to phi beta at x. So again, the positions on the manifold are related by a change of coordinates, and the vectors are just related by the derivative, just as we needed. Okay. Are there any questions um, on this? Because this is, like I said, this is the most important concept that I have introduced thus far after that of manifolds. Um,
So could you just say again why like magnetic field wouldn't be a vector?
yeah. So one of the reasons why it is not a vector is because the textbook I'm following says it's not. Um, but the more I guess the more physical reason is it doesn't transform as if it was a vector. So because of Lorentz transformations, right? Um, when I when I transform B under a Lorentz transformation, I pick up like extra stuff that doesn't transform like a vector in the case of like classical mechanics, right? So in this case, like E and B would not be vectors because they sort of intermix in a non-trivial way um, under like change of coordinates. We'll see later on that the electric field is a one form and the magnetic field is a two form.
Okay, very good.
Yeah, and then if you've ever heard of the electromagnetic, sorry, the Faraday tensor, like F mu nu, um, F mu nu is a two form. So this is again just an aside. If you've taken 450, like physics 450, um, F mu nu, like the tensor F mu nu, is actually um, so F mu nu is a two tensor. It's actually a two form given by this. Okay. Um, and in coordinate independent way, this is B plus E wedge GT.
Wait, sorry. So when you say it's a two form, like I can see how it's a two form this way, but
Mhm.
is F mu nu itself a two form, or is it only F mu nu dx
This F
mu
mu nu?
wedge? Yeah.
These F mu nu are just components of the two form.
Okay.
This whole
So we
thing.
would write it as F mu nu, but what we really mean is the components of it.
Yeah,
Like
yeah,
when
yeah,
we see F mu nu, we're actually talking about components
yeah. So if
rather
it
than okay.
again,
Oh no, I guess that makes sense because we'd be summing over it, right? Usually.
yeah, yeah. So for example, you might see situations like this, which show up in the electromagnetic action, right? Here, what you're doing is you're tracing over the mu component and the mu component. Okay. So this itself is not the tensor. It's rather the components of the tensor being added up together. So you have an implicit sum over mu and nu here. And we'll see that um, B and E are not really tangent vectors. They like transform weirdly. Um, and because of that, they're like more exotic objects. Well, they're not actually more exotic. They just feel like they're more exotic because we haven't worked with them all our lives. Okay. So are there any questions on this? Now, we're gonna take a step back because a lot of what we've talked about is extremely abstract. Um, and I'm I'm gonna go in a different order than what I have in the lecture, like in my meeting plan. Um, and let's just for a second talk about the tangent bundle, um, and why it's useful. So we already saw one place where it's useful is we can figure out what things are Lie groups and what are not. So we know that S2 cannot be a Lie group. Okay, there's no way for S2 to be a Lie group because its tangent bundle decomposes weirdly. If I am not mistaken, this is because of something called the Hairy-Ball theorem, which you may or may not have heard of. Um,
Well, I've heard of it.
yeah, so the Hairy-Ball theorem just says that there is no continuous vector field on S2 that never vanishes. Um, and now this is a very weird result, right? Like you would expect, I don't know, you would expect it to vanish. So you would expect there to be one that never vanishes, but it turns out that it's impossible. Okay. And it turns out it's impossible only in the even dimensions. So you can find vector fields that never vanish in odd dimensions, but you can't do that in even dimensions. And because of the Hairy-Ball theorem, what you can't do is you can't find vector fields, so you can't find tangent vectors at each point that are linearly independent, smooth, and smooth, right? Because if they were linearly independent at each point, they would be non-zero everywhere, which would then be a contradiction. Okay, so the tangent bundle cannot decompose like this. So given the Hairy-Ball theorem, so if you pretend like you know the Hairy-Ball theorem, we can look at vector fields now. What I claim is we can look at vector fields um, as tangent vectors. Okay. In fact, that's how we'll define a vector field on an abstract manifold, right? Is tangent vectors. Um, and if you could find a continuous vector field that never vanishes, then, sorry, sorry. Let me reorganize myself a little bit. So we have the Hairy-Ball theorem. Now suppose that we can find uh, two vector fields on S or on S2, um, so that they're linearly independent at each point. Because remember, we're saying vector fields are tangent vectors and whatnot. So they're linearly independent at each point. But what that would imply is that they're both never non-zero. They're both never zero, which would then imply that it contradicts the Hairy-Ball theorem. And so this decomposition is impossible. Okay. We will see that like the tangent bundle decomposes this way only if you can find vector fields so that they're linearly independent at each point. That's why these manifolds where the tangent bundle does decompose like this are called parallelizable. So M is said to be parallelizable. I don't know, it's something like that. Spelled something like that. Um, and that's mainly because you can find like tangent vectors at each point. Okay. So I've already sort of given away why we look at the tangent bundle, and that's because we can define vector fields. Okay, so a vector field on M is a map sigma, okay, from M into the tangent bundle. And now we want that the vector field be tangent to its point, right? Like we don't want it to be tangent to some other random point. So actually, can I even define vector fields or no? No, I cannot. Sorry. Oops. I've jumped the gun. Let me I need to define a vector bundle before I can define tangent bundles. Um okay, so then I'll have to go and that's why I laid out things the way I did. Um okay, so now with all this, let's now look at um what properties do um the collection of sets and the transition functions play, like what properties do these have that allowed us to define this equivalence relation in the first place. And if you want like the full um, treatment of why I'm just skipping the gun here, actually not the full treatment, what am I saying? If you want the full treatment of the subject without any steps skipped, um, please look at the principal bundle book that I like said in the beginning. But the properties are as follows. So we have a collection of sets that we'll call U alpha and maps G beta alpha from U alpha intersect U beta into some Lie group. Okay, so G here is some Lie group. Some Lie group. And in the case of in our case, this Lie group happened to be the general linear group of Rm, but there was nothing special about the general linear group. Also, there's nothing special about the map. There's nothing special about these transition maps, as long as they follow these three properties, such that, so one, remember we need X to be equivalent to itself, which means that G alpha alpha has to be the identity. Second, the inverse of um, the map beta alpha has to be G alpha beta. Okay. And thirdly, going from alpha to gamma is the same thing as first going from alpha to beta and then going from beta to gamma. Okay, so that's one way. So this has to be on this set, and this has to be on this set. Can you see why we need these three properties? Because we use these three properties, right? Like these three properties were very crucial in our proof of reconstructing the manifold from local data. So if we go back up here, we see that to show that X is equivalent to itself, we looked at the transition function psi alpha alpha. To show that X equivalent to Y is the same thing as saying Y is equivalent to X, we use the transition function psi alpha beta, which happened to be the inverse of psi beta alpha. And finally, to go from to show that X equivalent to Y, Y equivalent to Z means X is equivalent to Z, we made use of the transition function psi gamma beta. Sorry, we made use of the map psi gamma alpha. Okay, which happened to be a composition of psi gamma beta and psi beta alpha. Okay. These maps, right? These maps are called cocycles. Now, one thing I should mention is that we've only defined finite dimensional manifolds. Okay. Um, there's nothing wrong with that for the most part. However, there's a bunch of theory that you cannot write in terms of cocycles if you work over finite dimensional manifolds. Um, I'm unfortunately not too good at, like, I don't know much of the theory of infinite dimensional manifolds, so I'm not even gonna try to go in there. Um, but if we allow um, if we allow infinite dimensional Lie groups, um, what we can do is we can sorry, I lost my train of thought. So if we allow infinite dimensional Lie groups, um, we can generalize this notion of a cocycle to more general to a more general type of manifold. Sorry, to a more general type of construction. Um, so in this case, the tangent bundle, the Lie group for the cocycle was the general linear group. Um, but there's nothing special about the tangent, like tangent space. You could take any vector space, right? You could take any vector space, and then you could um, let your cocycles be the general linear group. So you can let your cocycles be on the general linear group of that vector space. And what you would get is something called a vector bundle, right? So if G were equal to GLV, then we would have a vector bundle. Okay, a vector bundle. I'll give a more like I'll give a I'll give a more concrete definition or more general definition of a vector bundle in just a bit. if G was the diffeomorphism group of a smooth manifold, then we would get something called a fiber bundle. But we don't really have too much use for fiber bundles as of yet. All we care about is vector bundle. So let's now define a vector bundle. So one way of defining a vector bundle is using cocycles. So you take the same thing we did with the tangent space, sorry, the tangent bundle. You do, but now what you do is you take your sets to be like some arbitrary vector space. Um, you take your set to be some arbitrary vector space, then you give transition functions on, um, the products of those vector spaces with your original space, and then you give some transition functions between those to glue the sets together. Um, so if we did this more generally, we say so let me actually make this a definition. So let pi from E to M be a smooth surjection. So since it's a smooth surjection, E and M are both smooth manifolds. Sometimes we require that the derivative of pi be surjective. If that condition holds, we say pi is a submersion. Okay, so pi is a submersion if d pi p from TPE into T pi p m is surjective. Is surjective. Yep. So if you have such a smooth surjection, then E is said to be a rank K vector bundle over M if. So there are certain properties that we require. Um, one, or one, um, sorry, I've lost my, oh yeah, okay, so one, um, for each P and M, the fiber pi inverse of P, which I will call EP, is a k-dimensional real vector space. Yep. So again, we saw this in the definition of the tangent bundle. The fiber at each point is the tangent space, and the tangent space is a real, like real vector space. So this is not something surprising. Um, and then another thing is um, for each P and M, there is a open set U containing P and a diffeomorphism phi from the preimage of U into U cross Rm. So it's a diffeomorphism, and pi restricted to U composed with phi. I feel like there's a mistake there. Okay. Let me write it like this actually. This where pi of U goes from U times R M into U is the trivial projection onto the first component. Um, so we have the condition that project which projection you use doesn't matter. And the other thing is that phi restricted to EP from EP into R, this should be K. Oops. K is a vector space isomorphism. Okay, so in the case of cocycles, as we see that our cocycles take elements in the general linear group, okay, um, of the vector space. So you can't actually, I'm being very hand wavy with that. You can't actually say that because the maps from EP into RK don't actually form a group. Um, because you can't compose those maps together or whatnot. But you can pretend that EP is actually just RK, right? Because the vector space itself doesn't actually make too much of a difference. Like what the vector space is very inconsequential, right? Because it doesn't affect the topology. Um, it doesn't affect the cocycle conditions. It doesn't affect the definition of a vector bundle because as long as a vector space isomorphism, it doesn't matter which vector space you're putting there, as long as it is a vector space. So a lot of the cases, what we'll do is we'll just like we'll stick in copies of like Rn, um, and then we'll call it a vector bundle because it doesn't actually matter like what the vector bundle is. But this is a slightly upsetting that this has to be the case. So one workaround is you can one workaround is doing what I said you do, right? Just put in Rn and copies of Rn everywhere. But another thing you could do is you can take a representation of G. Okay. So um note we may take a representation of G, representation rho, okay, of GL Rn um to get the following. So we have our like atlas and whatnot. Um, so then we can let E equal the disjoint union, um, in the usual sense, like this. And then we can quotient out by the equivalence where phi alpha x v, right, is equivalent to G beta alpha of phi alpha x v, which if I just write everything out, just equals rho of G beta alpha at x times b. Okay. So this is another way of defining a vector bundle. You can take the cocycles, um, then choose a representation of the group that you want to work with, um, and then define the equivalence like this. We will actually make use of this definition of a vector bundle when we talk about principal bundles. Um, and yeah, are there any questions on what a vector bundle is? Okay. So I'll just define one last thing before we leave for the day. Um, and that's to come back to the tangent bundle and define a vector field finally. Um, so note, note that if you have a tangent vector xp at TPM, then xp is nothing but some coefficients times partial. How do I want to write this? I'll be very so okay. So you pick a point in the tangent space. You pick a choice of coordinates on P or like around P. And then as we defined last time, this is how your tangent vector is defined in these coordinates. Um, and if you recall, when we do a change of coordinates, the what hap we'll talk about this more next time, and we'll see why we wanted this definition of the tangent bundle. Um, but just for the sake of non-cumbersome notation, I'll just write it like this. Okay. Even though the xi coordinate vector field here is not the same as this thing, just for notational sake, we'll do that. Um, and then in this case, what we'll do is a vector field on M is a map sigma from from M into the tangent bundle such that um, if I do sigma and then I do pi, I want to be tangent. So P wants a tangent vector at P. P does not want a tangent vector at Q. So all this says is that this is the identity on M. Okay. So this is all a vector field is. At each point, you give me a tangent vector. Okay. This map is also called a section. So, so if we have a vector but vector bundle pi e m, then a map sigma from M into E is a section if pi composed with sigma is the same thing as the identity on M. Moreover, and now a smooth vector field is just a vector field that is smooth. A continuous vector field is a vector field that's continuous. A smooth section is a section that is smooth, and so on and so forth. Um, now heard me say, you've heard me talk about differential forms and stuff like that. Differential forms are also just sections of some vector bundle, as we will see. Okay. So to each, what am I saying? So the tangent bundle is the most important bundle because now we can define. So if we take the cotangent, say, if we take the dual space of each tangent vector, sorry, each tangent space, we can combine everything together to get a like cotangent bundle. Okay. And then if we just take the tensor products of tangent spaces and cotangent spaces, we can get another bundle, which will be the tensor bundles. And then we can talk about the exterior bundles and so on and so on and so on. So once we have the tangent bundle, we've really opened up Pandora's box. Okay. The construction of the tangent bundle is, in my opinion, the most important construction Um, one does because this sets the like if you understand how to construct the tangent bundle, there is no other vector bundle that would be confusing to construct. Okay, because the tangent bundle, the first time you see it, is the most unintuitive manifold there is, right? Because you would expect that the tangent bundle, just given the way it's defined, you can always parallelize your manifold, right? And that's just not true, as we saw with the case of the sphere. Um, and to the tangent bundle, on the tangent bundle, we define the Riemannian metric. We define associated bundles to the tangent bundle. Um, and integration theory is mainly possible because of differential forms. Differential forms are sections of the exterior bundles of tangent bundles. And so, yeah, okay, I've been rambling on, saying the same thing again and again. But the tangent bundle is the most important bundle that you will construct. Um, yeah, so are there any questions? Okay. Um, if there aren't any questions, then I will I'll call it a day for today, and then we will meet on Monday. Let me just stop the recording.